let's jump right into this explainer and tackle a universally relatable engineering pain point, the tightly coupled application. If you build software, you know exactly what I'm talking about, components that are just way too tangled together. Today, we're going to untangle them. We're looking at a concurrent publish-subscribe pattern in Go that fundamentally powers modern, scalable systems.
To really appreciate the solution, we got to look at the problem. Picture this. A user clicks a button on your app. You wrote the handler for this. At first, three things happen, right? The analytics system logs the event, the notification service fires a push notification, and the UI transitions to the next screen. Simple enough. But then, a week later, you add a fourth step, writing to an audit log. A month later, a fifth step for A/B testing triggers. Suddenly, your simple click handler is a 200-line mess of tight coupling. Every single time a new feature is added, you have to open up and risk breaking this exact piece of code. It's a nightmare.
And that brings us to the core solution, the publish-subscribe pattern. The absolute golden rule here is total decoupling. The button, our publisher, knows absolutely nothing about who receives the click event. It just publishes to a topic. And the subscribers? They don't know anything about the publisher, or even each other. They communicate only through channels. Think of it like a concert venue. The band is the publisher playing the music. The audience, those are our subscribers, and they only hear the music through the venue speakers, our channels. The band isn't walking around hand-delivering the music to each individual person.
Now we have to contrast this with the traditional synchronous observer pattern. In a sequential observer, if the button's click handler waits for every single subscriber to finish processing before it returns, your UI freezes under load. It's totally blocking. But this concurrent version, it gives us fundamentally different behavior under load. Each subscriber is running in its own Go routine. The publisher fires off events at full speed, completely concurrently, and never waits around for a slow subscriber to finish its job.
To build this out, we have to start with strict contracts. Think of the publisher interface like a secured Dropbox. Information only flows in one direction. Looking at the code, our add and remove subscriber methods return a chan_square subscriber. That little arrow is absolutely key. These are send-only channels. Callers can only send to them, they cannot receive. This is compile-time enforcement of our communication protocol, preventing any outside component from directly mutating the shared subscriber list. It perfectly sets up our communicating sequential processes, or CSP approach.
Now, in any event-driven system, you can't let one slow consumer hold up the entire pipeline. To fix this, if you look inside our subscribers notify method, we use a select statement paired with a time.after 1 second timeout. It's basically a channel send that either succeeds before the stopwatch runs out or it just returns an error. This 1 second timeout is a critical defense mechanism. It absolutely guarantees that a slow subscriber won't block our fast-moving publisher.
And speaking of defense mechanisms, what happens when a channel suddenly closes? Sending a message to a closed channel is a very real, everyday Go problem, and it will cause a system panic. Going back to our concert metaphor, it's basically like blowing out the venue speakers. To isolate the blast radius, we wrap the notify method in a defer-recover block. It's a real production technique that defensively catches the panic, ensuring the rest of the show goes on without crashing the whole system.
So how exactly does the publisher manage all of this state without getting completely tangled? Well, instead of direct state mutations, it exposes channels as its API. Think of them like pneumatic tubes sorting mail. Add requests, remove requests, and data seamlessly fly into the add, remove, and in channels, completely non-blocking from the caller's perspective.
All right, pay attention here, because this is the core architectural insight of the entire pattern, the start Go routine. Think of it as our dedicated venue manager. It runs an infinite for loop with a select block, listening to all those API channels. Because this one single Go routine exclusively owns the subscriber slice, no traditional mutexes or locks are needed. Let me repeat that. No mutex needed. All list modifications and broadcasts are serialized right through this loop. The select statement is the synchronization. But look, even expert code has sharp edges. The source material brings up a really fascinating teaching moment by transparently acknowledging a flaw in its own testing code. Identifying and naming these sharp edges, that's the true essence of engineering craft. So where exactly is the hidden race condition here?
It's right in how the test checks the subscriber count. Just like sneaking behind the venue manager's back, the test directly accesses the length of the subscriber's slice. By bypassing our carefully constructed single Go routine, it's reading shared mutable state while the publisher might still be broadcasting. This perfectly illustrates why for a production system, we absolutely need a demultiplex method. We need a channel-based request that politely asks the venue manager for the count, rather than bypassing them and counting the empty seats ourselves.
Let's move on to lifecycle management, specifically the cascading close. You know, Go routine leaks are the silent killers of concurrent systems. But watch how cleanly this shuts down. You send one signal to close the stop channel. That triggers the publisher Go routine to call close on every single subscriber. That in turn closes all of their individual in channels, which finally causes every subscriber Go routine to exit safely. One single signal cleanly cuts all the venue speakers and shuts down the entire system without leaving any ghost processes running in the background.
This cheat sheet perfectly summarizes our architectural defenses. Really, it's the difference between a system that crashes at 3 a.m. and one that just hums along perfectly. It maps the 3 most dangerous Go routine failure modes directly to the channel-based solutions we just talked about. If a slow subscriber threatens to block the publisher, we use select plus a timeout. If concurrent mutations threaten a race condition on the list, our single Go routine synchronization completely prevents it. And if removing a subscriber threatens a Go routine leak, our cascading close method ensures a clean, safe exit.
When we look at the evolution of system design here, the journey becomes super clear. We start with direct method calls, which are highly coupled, not concurrent, and very rigid. Moving to static channel fanouts gives us some concurrency, but it remains fixed. But when we transition to the concurrent pub sub pattern we've explored today, coupling drops dramatically to loose, while giving us a fully dynamic, concurrent event handling system that is absolutely perfect for scalable production environments.
To wrap things up, I want to emphasize that this isn't just some clever trick for Go programming. The pub sub pattern is the exact architectural heartbeat behind every major message broker. If you understand this single Go routine synchronization pattern, you literally understand the macro architecture of the world's biggest distributed systems, like Kafka, Redis Pub Sub, and AWS SNS. The principles of decoupling, concurrent processing, and defensive channel management apply everywhere. So I'll leave you with this question for your own work. How are you going to use this pattern to decouple and accelerate your next system?